Hey everyone, welcome back to AP Physics Review. We're going to do the FRQ now, so let's dive into it. Computer's the wrong way. Okay, here we have a mathematical routines FRQ. We are almost to the point where I feel like I can go over all the types of FRQs with you. But we're not quite there yet, so this is just referencing what's going to come later. There's 4 different types of FRQs. This one is the mathematical routines. It has mathematical in the name. It's gonna involve some derivations. So just know that. So let's start off. Let me full screen. All right, we have a pulley system here. We have M1 and M2, 2 blocks, mass. Block 1 has a mass of M2, so this one's mass is 2 times M. Block 2 has a mass of M, this one's mass is just M. They're attached together by a string that passes over an ideal pulley, which is a pulley without mass and without friction. The pulley has negligible mass and is free to rotate on its axis with negligible friction between the axle and the pulley. The 2-block pulley system is held by a force sensor. So we have a force sensor here. The force sensor is going to measure the tension force pointed up on the pulley here. The blocks are free to move. On the following dots that represent the blocks, draw and label the forces, not components, that act on the blocks. Each force must be represented by a distinct arrow starting on and pointing away from the dot. Alright, on the 2 mass block, there are 2 forces. We have a force of tension pulling up, and then we have a force of gravity pointed down. On the other mass, we have a force of tension pointed up. These 2 forces of tensions are going to be the same because it's the same rope and it's an ideal pulley. The mass of block 1, or I guess this is block 2, is also going to have a force of gravity, Fg. Let's distinguish these. Let's say this is Fg2 and this is Fg1. Fg1 is going to be twice as big as Fg2. In this first free body diagram, Fg1 is going to be bigger than the force of tension. On the second free body diagram, Fg2 is going to be less than the force of tension. Because we know that when the system is released, the system's going to move like that. Right? This block is going to move down simultaneously. This block is going to move up. Alright, starting with Newton's second law, derive an expression for the magnitude of the force that the force center, F of S, will read while the pulley is fixed in place and the system is at rest. So the system is not accelerating. The blocks are just stationary. Express your answer in terms of M and physical constants only. Physical constants meaning G. So M and G. Alright, whenever we're doing a derivation problem and it tells you an equation to base it off, please start off with that equation. F equals ma. We're starting off with Newton's second law. It says to start with Newton's second law, write down Newton's second law. There is a point just associated with writing down Newton's second law and starting a derivation with that. Meaning you can't just write Newton's second law, you do have to attempt to use it. But that's a really, really, really easy point to get. Even if you don't know what to do at all, that should be a point you should get. Alright, so I'm going to write another free body diagram, and we're going to do it about the pulley here. So if I look at this pulley has a couple forces acting on it. It has a tension force pointed up, and it has 2 tension forces pointed down, one from this rope and one from this rope. Now, these tension forces, when the system is at rest, these blocks are not moving. In other say, we're going to pretend like this pulley is not going to move. These blocks are just hanging like this. That means these tensions are going to be equal to the forces of gravity from the blocks, since they're just hanging, they're not moving. Which means we have 2 mg there, and we have mg there. The system is at rest, which means F net is equal to 0. There is no acceleration. And since F net is equal to 0, I can say that the force of tension pulling up is equal to 2mg plus mg down. The force of tension pointing up is equal to 3 times mass times gravity. And that force of tension pulling up, this force, is what the force sensor is reading. So the force sensor is going to be reading 3 mg. All right, next question. The pulley is released and the system begins to move with block 1 falling towards the ground. So we already said that was going to happen. Now the system is moving. This block is moving down. This block is moving up. Starting with Newton's second law, again, derive an expression for the magnitude of the tension in the rope. So the tensions are now going to be equal on these two blocks, just like we said in these free body diagrams right here. The tension is equal. And we'll have to solve for what that force of tension is, probably in terms of m and physical constants, so m and g again. All right, there are two ways to solve this problem, and I think it's worthwhile to do both ways. I'm going to start off with the way that I like better. So whenever I have a system like this with multiple blocks moving at the same time, I like to think of it as one system. So if I kind of unravel this system over here, then I'm gonna do this. We'll span this gap. So we have this 2m block, and this 2m block is connected to this m block. This 2m block is moving with a force of 2mg this way. Its force of gravity is pulling it to the left. This m block is moving with a force of mg this way. It has a force of gravity pointed in the opposite direction. So in other words, I'm saying that, let's unclutter this a little bit. I'm saying that this direction is the positive direction, which would be to the left over here. And then we have this force of tension in the middle. To find that force of tension, first thing I'm going to do is let's just find the acceleration of the system. So starting with Newton's second law, F net is equal to mass times acceleration. So the net force would be 2mg to the left minus mg to the right. The mass, since I'm looking at both blocks as my system, the mass is going to be 3 mg. And the acceleration of the system is a. That's ultimately what I'm trying to solve for. So simplifying the left, we have 2mg minus mg is just mg. That equals 3mg, or 3mga. I don't know why I put a g there. It's just 3ma. The mass does not include gravity. So mg equals 3ma. And divide both sides by 3m, we get a is equal to g over 3. Which checks out. It shouldn't be as big as gravity. It should be a number smaller than gravity, because if like block 1 here were to fall just normally, it would fall at the speed of gravity, at the acceleration of gravity. But it's also having to pull this other block up, so it's going to fall less than that of gravity. Next thing I can do is I can just okay, hold on. That's a little bit too much of a mess up for me to just ignore. Go back. Okay, next thing I could do is let's just look at either one of these free body diagrams, because the goal is to find this tension right here. And to find that tension, I need to pick a free body diagram that has that tension in it. So let's look at the smaller block. The smaller block, its free body diagram is just Ft up minus Fg down. So once again, F net equals ma. I'm looking at the small block. It has a force of tension. Stop. That's really lagging. It has a force of tension up minus mg going down, and that equals its mass m times acceleration a. So now we're just looking at the small block system. This block, this free body diagram. Force of tension up minus force of gravity of that block down equals its mass times acceleration. I now know what acceleration is. I can plug in acceleration. So I get Ft minus mg equals mg over 3. Plugging in g over 3 for acceleration. And now I can solve for Ft. Ft equals mg over 3 plus mg, which would equal, this would be, we can do 3 over 3 mg. It would be 4 over 3 mass times gravity. So that is my answer. 4/3 mass times gravity equals the tension. Let's do it another way. So this is the way I kind of most like to do it. It makes most sense to me to find the acceleration of the system, and once I find the acceleration of the system, I can just use any free body diagram that has force of tension and plug in that acceleration to solve for just the force of tension. The other way you can do it, I think, is the more AP Physics approved way. And it's looking, instead of the whole system, it's looking at both of these free body diagrams individually. So let's set up a Newton's second law for both blocks, starting with the big block. The big block has its force of gravity down and force of tension pulled up. So F net equals ma. We still have to start with Newton's second law. The net force is 2 times mass times gravity down minus force of tension up, and that equals its mass, which is 2m times a. For the second block, we've already done this free body, or this F equals ma equation. We have force of tension up minus mg equals mass times acceleration. Now, in order to solve for force of tension, we still don't have the acceleration here. So let's solve for acceleration in terms of one of these and then plug in into the other. So in other words, we have a system of equations here. We have two equations with two unknowns. What we should be doing is look to substitute out one of the unknowns with the other equation. So I'm going to solve this equation right here in terms of A. Just divide both sides by mass. A would equal force of tension minus mg over m. And I'm going to plug that A right here. So I get 2 times mass times gravity minus force of tension equals 2 times mass times Ft minus mg over m. And now it's about simplifying and solving for force of tension. So I can cancel out this m with this m. Let's rewrite it. 2 times mass times gravity minus force of tension equals 2 times force of tension minus 2 times m times g. I also distributed this 2 to both of those terms. I'm kind of running out of space over here. Let's move this over to the side. Let's add 2mg to both sides and add force of tension to both sides. So I'm going to move this force of tension to that side and this 2mg to that side. I'm going to get 4mg equals 3ft, combining like terms. And now I can just divide both sides by 3. Force of tension equals 4 over 3 times mass times gravity, which is the exact same answer we got before. Which is good, they match. So that means we did both of them correctly. It does not matter which one you choose to do for this question. As long as you started with Newton's second law and you ended up getting the correct answer, it works. Again, I prefer the first way, but I can absolutely see someone preferring the second way as well. It's up to you. All right, last question. A force sensor is reading the original spring force. We found that original spring force. That was 3mg, by the way. That was this question down here, that one. But is seen to change when the system is released. Indicate whether the spring force will increase, decrease, or decrease, and briefly justify why the spring force changes using physics principles. Okay, this question is a little bit weird. Why would the spring force increase or decrease when the system starts to move? There's still the exact same of mass beneath it, right? The answer is yes, there's still the exact same mass beneath it, but the system below it has an acceleration. If we look at this system again, When these blocks start to move, we have this mass of 2 mg moving down, or 2m moving down, and this mass of m moving up. The center of mass of this system is going to start to accelerate downwards. The center of mass is like somewhere in between this 2m and this m, but it's closer to the 2m because it has more mass. So since the 2m is accelerating downward and the m is accelerating upward, the center of mass of the system ultimately ends up accelerating downward. This behaves a lot like the elevator problem that we looked at. Remember the elevator lab when we said when we had an elevator and we had someone standing on a scale. When the elevator was moving at a constant velocity or not moving, then the scale read the person's weight. But let's say the elevator was accelerating upwards. If it was accelerating upwards, all of a sudden, the person's weight doesn't change. However, the normal force increases because the normal force has to increase in order for the elevator to start accelerating upwards. The scale measures the normal force. So when it's at rest, the normal force equals the force of gravity, no problem, but when the elevator started accelerating upwards, that means the scale started reading more than the person's mass. For this spring scale system, all of a sudden we have a net acceleration downwards. We still have a net force downwards of 3 times mass times gravity. The masses of the blocks don't change. However, the spring force, the spring scale, is measuring this force of tension pointed upwards. And since this system is accelerating downwards, now all of a sudden, this 3 mg needs to be greater than the force of tension for this free body diagram to imply that the system is accelerating downwards. Which means the spring force decreases. The force that the spring, or the force that the scale, I keep saying spring, the force that the scale is reading is this normal force, and that normal force decreases. We have to justify that using physics principles. You can use drawings in your justifications. I would do that with this one. I don't want to do that. I don't want to write that all down. I just spoke it out loud, so I won't. Also, I got to go pick up my wife from Grills. So that is it for the free response questions. Let me text her, tell her I'm busy doing physics. No, I'm going to tell her I'm on my way soon. So, hope that helped. Let me know if you have any questions. And I will see you back in class on Monday, test on Tuesday. All right, see ya.